Hello and welcome. Today we shall see how to draw the frequency response of a system from its transfer function approximately. And this method will be applicable when the transfer function is of this form, that is the ratio of two polynomials of S. And recall that when the output-input relation of a system can be represented with a differential equation like this, then the transfer function will be of this form. We have seen this yesterday. Now, to get the frequency response from this transfer function, we will do the following. First, we will factorize these two polynomials like this. The numerator I will write as am, then s minus say z1, s minus z2 dot 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 up to s minus zm. Okay, where z1, z2, zm, these are the roots or solution of the equation that this numerator is equal to 0. If you set the numerator equal to 0 and find the solution or roots of this equation, then those are represented as z1, z2, zm. And since this is a m degree polynomial, we will get m roots or solutions, and you can factorize this in n factors like this. Okay? In the same way, the denominator can be factorized as s minus p1, s minus p2 dot 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 s minus pn. We will have n factors because the degree of the denominator is n. Now you know that p1, p2, pn, these are called poles of this transfer function, and similarly z1, z2, zn, these are called the zeros of this transfer function. So this factorization is step number 1. Then next, step 2, we will find Fourier transform of ht, impulse response, that is equal to capital H of j omega. Of course, this Fourier transform must exist, and for example, if we assume that all the roots in this denominator polynomial, that means the poles, have negative real part, then when you take Laplace inverse, you will get all exponentially decaying terms, and therefore ht will decay to 0 after some time, and it will be square integrable and Fourier transform can exist. So then hj omega will be equal to the same thing, but s replaced with j omega everywhere. J omega here, here and everywhere. This is the Fourier transform of Ht. Next, we want magnitude of Hj omega, that is mod Hj omega, and that is equal to magnitude of Am, magnitude of these terms j omega minus z1 dot dot dot, then j omega minus zm whole divided by magnitude of j omega minus p1, j omega minus p2 dot dot dot, j omega minus pn, and the angle or phase of h j omega, that will be equal to angle of Am, then plus angle of j omega minus z1 plus angle of j omega minus z2 plus dot 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 plus angle of j omega minus zm. This is from the numerator, and then from the denominator we will get minus angle of j omega minus p1 plus angle of j omega minus p2 dot 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 plus angle of j omega minus pn. Okay, next step 4, we will draw a diagram which is called pole zero diagram. We will draw a complex plane, Argand plane. This is real axis, imaginary axis, and then this z1, z2, zm and p1, p2, pn, these are complex number in general, okay, with a real part and imaginary part. Therefore, we can identify their location in this complex plane, Argand plane. Okay, so first, these roots of the numerator polynomial or zeros, we will draw their location on this diagram with symbol 0, like maybe z1 is here, z1, maybe z2 is here, z2, maybe z3 is here, z3, etc. So we will place them in their proper location. In the same way, these poles p1, p2, pn, they are also complex numbers, so we can put them in this diagram, and we will denote them with the symbol cross. Maybe this is one pole p1, maybe another pole is here p2, another is here p3, etc. Now, one important thing to note is this: poles and zeros occur in complex conjugate pairs. That means if there is a pole p2 here, which is a complex number, then there must be another pole p3 which is complex conjugate of p2. So that means the imaginary component of p3 is negative of imaginary component of p2. So they will be in mirror position of each other with respect to this horizontal axis. Same is true for zeros. Zeros must also occur in complex conjugate pairs. Either they are completely real like this Z1, this is completely real, there is no imaginary part, but Z2 has an imaginary part, so this is a truly complex number with an imaginary part. So there must be another zero Z3 which is complex conjugate of Z2. So poles and zeros are either purely real or they occur in complex conjugate pairs or purely real. Why this is so? Because look here, if these zeros occur with complex conjugate pairs like Z1 and Z2 are complex conjugates, then when you multiply this S minus Z1 and S minus Z2, you will get a quadratic polynomial, something like S square minus or plus some AS plus B, where this A and B will be real if Z1 and Z2 are complex conjugates. But if they are not A, B, they can be complex numbers. So if these zeros occur in complex conjugate pairs, then when you multiply them all, then you will get this this polynomial. There all these coefficients will be real number, and that is necessary because we are getting this transfer function from this differential equation, and for a real practical system, the governing equations, the governing input-output relations must have coefficients which are real, because in practical life we cannot have any physical quantity which is complex. So all these numbers which represent some physical fact, some physical quantity, they are real. Okay, so therefore only if these zeros occur in complex conjugate pairs, then here these coefficients are going to be real. Otherwise these coefficients will be complex, and that cannot come from any differential equation which describes a practical real system. And same is true for the denominator. These poles also must occur in complex conjugate pairs, or they should be purely real. Then when you multiply them, then these coefficients bn minus 1, b1, b0, they will be real, and that is necessary because that is coming from a differential equation describing a real practical system. Okay, great. So now we have this pole zero diagram, and from this we will draw magnitude and phase spectra. So omega versus mod of h j omega, and another diagram omega versus angle of h j omega. Okay, now here is the idea. Let us first consider the magnitude. The magnitude is product of all these terms, where this am is like a constant, it does not depend on omega at all, so you may plot am like a constant. So this is am, mod of am. Okay, then consider the next term, j omega minus z1. Okay, now this is a term that depends on frequency omega. Okay, so let us consider mod j omega minus z1. Now if you are considering a particular value of omega, say omega naught, some particular value of omega here, and we want to get the magnitude response at this point, then this omega naught can also be marked in this pole zero diagram somewhere on the imaginary axis. Suppose this point represents j omega naught. Okay, then the magnitude at this point will be j omega naught minus z1, and this quantity j omega naught minus z1 is represented by this vector starting from z1 up to j omega naught. This vector is j omega naught minus z1, and the mod of that is the length of this vector. Okay, so you can measure this length in this pole zero diagram, and then this length you can put, so this length is this much, so you go up by the same amount here and mark this point. So this is the magnitude at this particular frequency value. Now if you consider some other frequency, say here omega, or say here say omega 1, and we want to know the magnitude at this point, then we will put omega 1 here, and then here also this point can be found somewhere here on the imaginary axis. Suppose this is j omega 1, then this vector, this is j omega 1 minus z1, and the length of this vector will be the mod of this quantity. So we will measure this length and accordingly mark that here somewhere. In this way, for different values of omega, we can get this quantity j omega minus z1 for any omega in general. Particularly say when omega is 0, that point is here, so this is the length then. Okay, and we will mark this length here, and here. Okay, and in this way we will vary the value of omega starting from 0 up to infinity, and we will check these lengths, this length, then this length, then this length, etc. We will vary omega and measure this lengths and plot it here. And as you can see, when omega is 0, in this case this length is minimum and then it increases. So this plot will be like this. It is minimum and then it increases and it will tend towards infinity. Okay? In the same way, you can consider for negative omega value like this, and in this diagram also you will get a magnitude response which increases towards minus infinity, increases towards infinity like this. So this is the diagram for j omega minus z1. In the same way, so you can plot j omega minus z2, zm, all other terms. Okay, and then you have to multiply all these terms. Okay. Suppose Z2 is here. So if we now consider, say, j omega minus Z2 mod of that, then you have to draw vectors starting from here up to different omega values, like this, then this, then this, like this, and so on. So you can see that for omega equal to this much, somewhat like this much, this length is minimum. Okay, this length is minimum, and maybe it is like this. And then when omega increases, this length increases, and on the other side also the length increases. So this is the plot. This is the plot for j omega minus Z2. In this way you have to plot these terms for Z1, Z2, Zm, all of them, and then multiply them together. Also you have P1, P2, Pn in the denominator, so you have to do the same thing and then divide these terms. Okay, so that's how you can plot the magnitude response from the pole zero diagram. Now let us look at the phase response. Now this phase, you can see here, is a sum of the phases coming from individual terms. Okay, so let us see how to plot the phase for j omega minus Z1. Okay, so we want to plot first the phase or angle for j omega minus Z1. Z1 is here, and you pick any particular value of omega, say omega naught. You mark the same point here somewhere. This is j omega naught. Then you join this z with j omega naught. This vector is j omega minus Z1, and then this angle is given by this angle. So in this case you can see the angle is around 45 degree. So you can plot here that point, 45 degree. Then you have to do the same thing for different values of omega. Suppose I pick omega equal to omega 1 here, then you mark that point here, j omega 1, join these two, and now this angle is maybe around 30 degree, so you mark that point here, and in this way you vary the value of omega. And when omega is 0, it is here, then the angle is also 0. So here we will mark angle 0, and as you increase omega towards infinity, you can see that the angle also increases and it goes towards 90 degree in the extreme case. So this plot will look like this. It will reach 90 degree finally. Now in the negative side, when you decrease omega, angle also becomes negative and it keeps decreasing, and in the extreme case for omega tending to infinity, the angle will be minus 90 degree. So this plot will be like this, going to minus 90 degree. Okay, now very important fact, as you all know that this phase response curve should be antisymmetric, it should be a odd function, and that is what we or we are also getting from this process. In the same way, magnitude response should always be symmetric. Okay. Okay. So this is for j omega. This was for angle of j omega minus z1. Then after that, suppose we want the angle of j omega minus z2. That is the next term here. Okay. So then for that you have to draw vectors starting from z2 like this, so on, and you can see this angle will be 0 for omega close to omega naught. Somewhere here the angle will be 0, and after that the angle will increase. It will go towards plus 90. Before that the angle will decrease and it will go towards minus 90. So this plot is for angle of j omega minus z2. In the same way you can do this for z3. So for z3 you will get 0 degree somewhere here, somewhere around minus j omega naught, somewhere here 0 degree. After that it will increase. Before that it will decrease like this, and finally you have to add all these terms to get the total j omega. Okay. Also you have to do the same thing for the poles and subtract them. Then it will be complete. The next thing we will learn today is how to obtain transfer function for an electrical network or circuit. We will learn that with simple examples. So here is our first example, a very simple circuit which has one resistance R in series with a capacitor C, and this other end is grounded, 0 potential. Here I can apply a voltage V in t, function of time. So this is my system and this is the input to my system, and from this point I will measure the voltage at this point. Call it V out t, function of time. So this is input, this is output, and this is the system, and we have to find the transfer function Hs. What is Hs? Hs is Laplace transform of Ht, impulse response. What is Ht? That is the output of the system when input is delta t. So let me give delta t as the input. Yeah, this is a thought experiment, of course. Otherwise ideal delta t is not available in laboratory. So assume delta t is given as input, then the output will be by definition Ht, or whatever output we get, that is our Ht. Okay, now input is known, we have to calculate output, then we can take Laplace transform. How to solve this circuit? We can use the idea of solving a circuit in S domain that we have learned. Okay, so we will first redraw this circuit where we will represent all the quantities with their Laplace transform. So instead of V in t, I will write capital V in S. This is Laplace transform of this V in. Instead of delta t, you can write 1. Instead of V out t, write capital V out S. Instead of HT, write capital HS. And remember, this is done under initially relaxed condition, because that is the definition of HT. HT is the response of the system when the input is delta t under relaxed condition. That is the definition. Okay? Okay. And initially relaxed condition means what? Means this voltage is initially 0. So this capacitor voltage is 0 initially, and that means the capacitor had no stored charge previously, uncharged capacitor, and therefore we can represent the impedance of this capacitor as 1 over Cs. This will be the ratio of the current here and voltage across it. Okay, and the Laplace domain, S domain impedance of this resistance will be same as R. Then you apply any circuit theory that you know. So we will apply potential divider rule here. So V out S will be equal to V in S divided by the total impedance R plus 1 by Cs multiplied with 1 over Cs. Basically this part is the current that flows here. I mean the Laplace transform of the current, of course. And then this is the Laplace transform of output voltage, which is Hs. And V in S is 1. Okay, so Hs is equal to, let me simplify this, we will get 1 divided by 1 plus RCS. So this is the transfer function. Now we will try to plot the frequency response of this transfer function. Okay, so Hs is this. Let me write. Hs is 1 by 1 plus RCS. That means Hj omega Fourier transform of impulse response is equal to 1 by 1 plus RC j omega. Okay, and then you can use the concept of this pole zero diagram now, or you can do it even directly, because this is quite simple. So mod of H j omega, that will be 1 over root over 1 plus r square c square omega square, and angle of H j omega, that will be equal to tan inverse, the imaginary part is RC omega divided by real part, that is 1. This is the angle of the denominator, so angle of Hj omega will be minus of this. Okay, now let me plot here Hj omega, mod of that. So you can see as omega increases, this value increases, denominator increases, so the value will decrease, and at omega equal to 0 it will have maximum value. So it will be somewhat like this. and it is a symmetric function, of course, of omega, because we have omega square, so it will be like this. And then this angle of h j omega, when omega is 0, you see, then tan inverse 0 is 0, so here the angle is 0. Now if omega is very large, tending to infinity, then tan inverse infinity is 90 degree, and because of this minus, we will have minus 90 degree when omega is very large. Okay, so minus 90 degree, and that means as omega increases from 0 to infinity, this angle will decrease like this. Okay, and in the other half, when omega is negative, it will increase like this and go to plus 90 degree, because at omega minus infinity, this will be minus 90 and then minus sign, so it will become plus 90 degree. So this is the phase response, approximately hand drawn. So for a perfect drawing, you should calculate these values with different omega values put in these expressions. You can use a computer or a calculator and then plot these diagrams more accurately. Okay, and we could also use pole zero diagram. So let me also demonstrate that quickly. So real axis, imaginary axis, and HS is here 1 by 1 plus RCS. Let me write again. HS is 1 by 1 plus RCS, which is equal to 1 by RC common. Then I will write 1 by S minus 1 by RC in the standard form of S minus pole. So this pole is at minus 1 by RC, maybe somewhere here. Let me draw that with a cross. That is a pole. Symbol of pole is a cross, and this point is minus 1 by RC. Okay, now for different values of omega, okay, different values of omega along this axis, we will draw vectors like this, starting from this pole to a desired omega value. Okay, and this length is the length of the magnitude of S minus this. So you see, as omega increases, this length increases. So we will have a plot like this. And also for negative omega, it also increases. It will be like this. Okay, and but this graph is mod of j omega minus 1 by RC. Minus, so plus. Okay, but what we actually want is this mod of h j omega, that is 1 by RC, and mod of j omega minus 1 by RC. Okay, so this is in the denominator here. So this is not hj omega. Hj omega will be reciprocal of this. Hj omega will be 1 over this graph. That will be something like this. So here it is minimum. So when you take 1 over that, it will be maximum here, and then it will decrease. It will go towards 0. Okay. So this graph is of 1 by mod j omega plus 1 by RC. Yeah, we also have this constant RC multiplied. So this will be the pattern. Okay. In the same way, let us try to find the phase response. So phase response will be governed by these angles, this one or this one or this one, and you see that as omega increases, this angle increases. In the extreme case, it will be 90 degree. So that plot will be something like this. It starts from 0 here and then goes to 90 degree, and in the other side it starts from 0 and goes to minus 90 degree. However, this graph is angle of j omega plus 1 by RC. But what we want angle of h j omega, which is minus angle of this. So we have to take minus of this, and that will look like this. Like this. Okay. So this is the phase response, and you see previously also we got something similar. Now at this point I want to tell a very important thing, that is all LTI systems are nothing but frequency filters. What do I mean by that? Remember that any input xt can be broken into a sum of exponential signals like this, e to the power j omega t with coefficients capital X omega divided by 2 pi summed over all omega using Fourier transform, right? And then we know that these exponential signals are eigensignals of LTI systems. So when you give e to the power j omega t as the input to an LTI system, the output will be the same thing, e to the power j omega t, same signal with same frequency but multiplied with a constant which is h j omega, Fourier transform of impulse response. Now if the value of h j omega is large, then the output will be large. If this value is small, output will be small. H j omega depends on omega. For some value of omega, h j omega can be large and you will get large output. For some value of omega, h j omega can be small and you will get small output for same amplitude of input. For example, if you see in this system, we saw that h j omega, magnitude of h j omega is large for low frequency and very small close to 0 for large frequency. So to this system, if you give input of this form e to the power j omega t, you will get large output when frequency is small and small output when frequency is large. Also, you recall that e to the power j omega t are not practical real life signals. These are complex signals. But we also learned that if you give sine omega t as the input, then we will get sine omega t plus theta multiplied with m. M depends of course on omega. Theta also depends on omega, where m is nothing but the magnitude of h j omega, and theta is the angle of h j omega. So if this magnitude is large, if you give periodic sine or cosine input, you will get large output. If this magnitude is small, for some value of omega, you will get small output. So it seems like the system acts like a filter. Some frequency, some input frequency will give you large input. That means those frequencies can, as if they can pass from input to output, and other frequencies are blocked by the system. If you give those frequencies as input, you will get no output. Those frequencies are blocked by the system. So this system acts like a filter. It allows some frequencies to pass from input to output, and it blocks other frequencies. So systems are filters. Now let me just tell you some standard terminologies. Suppose you have a system whose magnitude response is like this. It is high for low value of frequency and low for high value of frequency. Then we call it a low pass filter, which passes low frequency from input to output and blocks high frequencies. Then if you have a system whose magnitude response looks like this, we call that high pass filter, because it allows high frequencies to pass from input to output and it blocks low frequencies. Then if you have a system whose magnitude response is like this, which allows a particular range of frequencies or band of frequencies to pass from input to output, we call that band pass filter. So all systems are filters. For example, this electrical circuit that we have discussed, it is a low pass filters, as we can see from the magnitude response. It is also clear from the physical consideration of this circuit. You think of the AC impedance of a capacitor that we represent by 1 by j omega. Okay, this is the impedance for pure sinusoidal voltages, And you see that when omega is large, this impedance is small. Now you think this as a potential divider. Here is one impedance, here is another. They are in series. Input voltage is here, output voltage is here. Now if this impedance is high, then output voltage will be high. If this impedance is low, output voltage will be low. And you see, when omega is large, this impedance is low, so output voltage will be low. That means for large omega, output will be low. So that means for large input frequency, we will not get much output. But for small input frequency, low input frequency, omega is low, this impedance is high, we will get large output. Okay, so now let me give you some homeworks. Take this circuit where you have a capacitor and a resistor. Okay, this end is grounded. Here input is V in T, and from here we will measure the voltage. This is our output, V out T. Your task is to find the transfer function Hs, then plot frequency response, and so that this is a high pass filter. It is a high pass filter. Okay, great. Next, consider these two circuits. This is a RL series circuit. This end is grounded. Here you can apply voltage V in input, and from here you measure the output voltage. Okay, task is again same. Find Hs, plot the frequency response, and so that this is a low pass filter. Also here, if you change the position of R and L, if you give input V in T here, and if you measure output from here, then find the transfer function, plot the frequency response, and so that it is an low pass filter. I'm sorry, this one is high pass filter. This is a high pass filter, this is a low pass filter. Okay, great. Next, I will show you some examples of similar problems, and I will do this quickly without explaining too much, but focusing on how to solve this type of problems quickly. Okay, so this is a circuit, series LCR. Here input voltage is applied V in T, and from here we get output voltage V out T. Our task is to find the transfer function and plot the frequency response. Okay, so first we will write all quantities in terms of their Laplace transform. V in S, here V out S, and all these impedances will be represented by their Laplace domain impedance. So for a resistance it is same as R, for a capacitance it is same as 1 by Cs, and for a inductor it is same as Ls. This is true under initially relaxed condition, but anyway transfer function is defined only under initially relaxed condition, so we can write this. Okay, then we need HS, but you recall that we have learned output, Laplace transform of output is given by HS input for any system. So HS can be written as V out S by V in S. So we have to find this ratio. Now in this circuit, if you call this current as IS, then V out will be equal to R multiplied with I, so RIS, okay, divided by V in S. Now this is equal to R. Now I is given by input divided by total series impedance, so that is V in S divided by Ls plus 1 by Cs, Ls plus 1 by Cs plus R whole divided by V in S. Okay, so then this will be equal to R, this V in cancels, we will get R divided by this quantity Ls plus 1 by Cs plus R, which is same as R divided by LCS square plus RCS plus 1 and then CS here. Okay, this is equal to S square plus RCS by LCS, so that is R by Ls plus 1 by LC, and numerator will be R by Ls. Okay, so this is the transfer function. Now we want to plot approximately the frequency response. So first we will write Hj omega, that will be equal to this thing with S replaced with j omega. So that is R by L j omega divided by j omega square is minus omega square plus r by L omega multiplied with j plus 1 by L C. So now the magnitude of h j omega, that will be equal to magnitude of the numerator r by L constant, magnitude of omega divided by 1 by LC minus omega square, the real part squared, plus the imaginary part r by L omega squared under root this. Okay, and the angle of h j omega, that will be equal to the angle of the numerator is 90 degree, okay, then minus angle of the denominator, that is tan inverse r omega by L imaginary part divided by 1 by LC minus omega square. Now let me plot the magnitude response approximately. So at very low frequency omega, very low omega, in the denominator you can ignore this term compared to 1 by LC, because omega tending to 0, very low frequency, and this is a finite number. So denominator is something constant and numerator will also go towards 0. So at very low frequency gain will be, this magnitude will be 0, and at very high frequency, when omega is very high, then in the denominator you see we will get omega to the power 4. There will be one term with omega to the power 4, that will be the dominant term, and that is under root. So denominator will have omega square dominating, numerator has omega, so denominator will be larger. So then at very large frequency this magnitude will again be 0, and somewhere in between, when omega square is equal to 1 by LC, that means omega is 1 by root LC, then this term will be 0, this will vanish, and from here you will get omega, one omega term in the denominator, and there is 1 omega in the numerator. They will cancel and you will get some finite number. Okay, so near this point you will get some finite gain. Okay, do it thoroughly, you will realize that. So the plot will be somewhat like this, and since this must be symmetric, it will be like this. So this is a band pass filter. I will leave it as a homework to plot the phase response yourself approximately. Okay, so this is a band pass filter. Next example, consider this circuit. We have an LC parallel combination in series with a resistance R. This end is grounded, that is the reference point. Input voltage is applied here, output voltage is measured from this terminal. Task is same, to find the transfer function of this system, plot the frequency response, and find out what kind of a filter is this. Okay, so we will first replace all time domain functions with their Laplace domain equivalent. V in S, capital V out S. These impedances will also be replaced with their S domain equivalents. R is R itself, L will become Ls, C will become 1 by Cs. This is under relaxed condition, of course. Then we have to find the transfer function Hs, which is V out S output divided by V in S. Now V out S, this voltage here is equal to R multiplied with this current, call this Is, RIS. Now this is equal to R, Is is V in S, this voltage divided by the total impedance, that is R in series with L and C in parallel. So R plus Ls parallel 1 by Cs. Okay, so that is equal to R V in S divided by R plus product of these two, that is L by C divided by sum of these two, Ls plus 1 by Cs. Now you have to simplify it. So this is R V in S divided by R plus, let me write this as LCS square plus 1, and this will be Ls. Now this is RLCS square plus R plus Ls, and above we have RLCS square plus R multiplied with V in. So HS will be V out by V in. This is V out. If you divide this with V in, you will get RLCS square plus R divided by RLCS square plus Ls plus R. You may now simplify it if you want. S square plus 1 by LC divided by S square plus 1 by RCS plus 1 by LC. Okay, please check my calculation if it is correct or not. Then you have to put S equal to j omega to get the Fourier transform of HT. That will be minus omega square plus 1 by LC divided by here 1 by LC minus omega square plus J by RC omega. Okay, from this you can get the magnitude, that will be this numerator as it is 1 by LC minus omega square, magnitude of that, divided by root over this quantity 1 by LC minus omega square whole square plus this quantity omega by RC whole square, and the angle of HJ omega, that will be the angle of the numerator, so that is a real number, so that can be either 0 or 180 degree, depending on this is positive or negative. So angle of 1 by LC minus omega square, then this minus the angle of the denominator, that is tan inverse omega by RC and divided by this, that is 1 by LC minus omega square. Okay, let me write it cleanly. Please check my calculation. Now you can put different values of omega starting from 0 to infinity and minus infinity, get this angle and this magnitude for different values of omega and plot them as a graph. Take a calculator or a computer if you like, or you can do that approximately with pen and paper. That is your homework, and then from that find out what kind of a filter this is, and the answer will be interesting. Thank you.